Okay, today we are taking a look at inequalities in one triangle. We will be taking a look at the triangle inequality theorem, which is about figuring out what measurements of side lengths actually allow us to form a triangle. And then we'll take a look at some other statements dealing with inequalities and just one triangle. So the very first thing we have is the triangle inequality theorem. The triangle inequality theorem says that the sum of the lengths of any two sides of a triangle are greater than the third. So, more simplistic version of this would be add the two smallest sides and if they are larger than the longest side, you can form a triangle. So the book's definition says the sum of the lengths of any two sides of a triangle are greater than the third. I much prefer saying that if we take the two smallest values, add those together, as long as the sum of those numbers are larger than the third side, you would be able to make a triangle out of that. So here we have two examples, and we'll actually go over a third example. So the first one is we have side lengths of 3, 4, and 5. So if I want to determine whether I can make a triangle, I take the two smallest, 3 and 4. You add those two numbers together, and you get 7. Well, 7 is greater than 5, and because 7 is greater than 5, yes, you can make a triangle. On my second example, I have 5, 10, and 15. I take the two smallest numbers, 5 and 10. I add those together, and you get 15. Well, 15 is equal to 15. Because 15 is not larger than 15, it is not possible to make a triangle. So another example would be, say we have 7, 3, and 5. So if we have 7, 3, and 5, what I have to do is take the smallest numbers. So 3 and 5 are the two small numbers, so I would add those two numbers together. I wanted to go over this example because in my previous ones, they were in increasing order, so we always just took the first two numbers, but it's the smallest numbers that we want to add. So you get 8. Well, 8 is larger than 7, so yes, this would be a triangle. So all you have to do is add the two smallest numbers. If the smallest numbers have a sum that's larger than the largest side or longest side, then you can form a triangle. So now, let's say that I want to find out what the range of possible side lengths would be. So let's say I'm trying to build a triangular sandbox. I have a 5-foot and an 8-foot piece of lumber. I am trying to find what is the possible sides that would allow me to make a triangular sandbox. So what we're going to do is I need to find out what the maximum and what the minimum values would be. So what's the largest and the smallest? So if I want to find what is the largest, I can take 5 plus 8, and this value has to be larger than whatever my unknown is. So whatever my third piece is, we're going to label that as x. So 5 plus 8 has to be larger than x. When you add those together, you get 13 is greater than x. Well, generally I like reading it as x first, so we go ahead and flip this around. So x is less than 13. So x has to be smaller than 13 feet to be able to make a sandbox. Well, what's the minimum? So now, if we're going to do the minimum, we're going to take and assume that 8 is the longest piece. So we would say 5 plus my unknown has to be greater than 8. So the two smallest pieces, we're going to assume 5 and the unknown are going to be the small pieces, and this would be the largest piece of the triangular sandbox. Then we just solve this inequality. So you just subtract 5 from both sides. You get x is greater than 3. So what that means is that as long as I buy something that is larger than 3 and smaller than 13, then I'm able to make a sandbox. Anything, if I bought something that was 3 feet or something that was 13 feet or anything that was smaller than 3 or larger than 13, you're not going to be able to make a sandbox out of that or a triangular one. So here's another example. We have a side length of 2 and 12. So take a little bit of time, see if you can find out the varied dimensions that would allow you to make a triangle with those values. So we have 2 plus 12 has to be greater than x. We're going to find the longest side, and then we would also say 2 plus x has to be greater than 12. This is saying that 12 is the longest side, so we're finding out another small dimension. Then we're just going to solve both of these. So 14 is greater than x, which means that x would have to be smaller than 14. And then over here you would subtract 2 and get x has to be larger than 10. So between 10 and 14 would be the possible dimensions. So the next thing we're going to take a look at is theorem 5-10, which says that if two sides of a triangle are not congruent, then the larger angle lies opposite of the longer side. So what this means is that if I have a triangle and I know that my sides are not all congruent, so let's say that I have, this is 3, and then maybe we'll make this 5, and then we'll say that this side is 7. And then we'll label this as triangle A, B, and C. What I can do is, by looking at the sides of my triangle, I can determine which one of my angles would be the largest. So it says that XZ is greater than XY. So if you know that XZ is larger than XY, then Y, which is opposite of XZ, is larger than angle Z. So in my example, 7 is the longest side. Well, because 7 is the longest side, the angle, which is B, which is across from side 7, would be the longest or largest angle. So the angle B would be the largest. So then if I want to find the next largest, or the middle, 5 is the second largest number. Well, 5 is across from angle A, so then angle A would be the middle. And then that would leave us with 3 is the shortest side, C is across from that, so angle C is the smallest angle. So here's an example. We have a town park is triangular. A landscape architect wants to make a bench at the corner of the largest angle. So I have Hollingsworth Road is 175, MLK Boulevard is 105, Valley Road is 120 yards. So where should I put my park bench if it needs to be at the largest angle? Well, the largest angle should be opposite of the longest side, and Hollingsworth Road is the longest side, so I should put it at the corner of MLK Boulevard and Valley Road, which is down here at angle B. And then it says, suppose the landscape architect wants to place a drink fountain at the corner of the second largest angle. So now I'm trying to find the second largest angle. So where is the second largest angle? So I'm looking for the second longest side. Well, 120 is the second longest side. Opposite of that is angle A. So we would say A would be where we want to make the water fountain. Okay, so now we have theorem 5-11, which just says the exact opposite, or it's the converse of what we were using previously. So now I'm saying that if I have a triangle, and we'll just make this real simple to start out with, we'll say that this is 30 degrees, we'll make this 60 degrees, and then we'll make this 90 degrees. So say I have a triangle that's 30, 60, 90. We'll label this as X, Y, and Z. So if I want to find the largest or the longest side, it should be opposite of the largest angle, which when you've dealt with a right triangle before, we always say the hypotenuse is opposite of the 90 degree and the hypotenuse is the longest side. So in this case, 90 degrees is the largest angle. Well, XZ should be the longest side. So XZ should be the longest side. Then if I want to find the second longest, well, 60 degrees is the second largest angle. So across from 60 degrees is YZ. So that means that YZ should be the middle. And then finally, 30 degrees is the smallest angle. Opposite of 30 degrees is side XY. So XY would be the shortest side. So we're kind of doing the same thing we were doing with the sides previously, except now we're looking at angles, and based off of the angles, we can determine what sides are the longest or the shortest. So go ahead and take a little bit of time, see if you can find out the order or which one of these A, B, or C or D is the correct order from shortest to longest. So to be able to do this, the first thing we have to do is I need to find out what this missing angle is. Well, luckily I have two of the three angles, so I can go ahead and add these two numbers together. So 58 plus 62 should give you 120. You'll subtract that from 180 because all triangles add up to 180, which will give you 60 degrees, which means that this angle, T, is 60 degrees. So now I'm going from the shortest to the longest side. Well, 58 is the smallest angle, which means that the side that is opposite of 58, TV, should be the shortest side. So let's see, D has TV first, C doesn't work, B doesn't work, so it's either A or D. So then we have 60 degrees, which is opposite of UV, so UV should be next, so should go TV, then UV. Well, this goes TV, UT, so that's not right. Well, this goes TV, UV, and then just to double check, we have 62 degrees. Well, opposite of 62 degrees is UT, which matches there, so A would be the correct order from shortest to the longest for this triangle. Okay, and the very last corollary that we're going to go over is it's a corollary to the triangle exterior angle theorem. So if you think back, we went over something that was known as the triangle exterior angle theorem. And the triangle exterior angle theorem said if angle 1 is an exterior angle, then the measure of angle 1 is equal to the measure of angle 2 plus the measure of angle 3. It just said that the remote interior angles are equal, or the sum of the remote interior is equal to the exterior angle. That's what we had for the triangle exterior angle theorem. Well, now what we're saying, a corollary, is taking something that we've done previously and made a slight variation on. Well, if I know that the measure of angle 1 is equal to the measure of angle 2 and the measure of angle 3, I should also be able to state that the measure of angle 1 is larger than the measure of angle 2. I should also be able to state the measure of angle 1 is larger than the measure of angle 3. The reason is that I have subtracted one value from this right side and done nothing on the left side, so therefore my inequality is no longer true, or my equation is no longer true. It is now an inequality. So the measure of angle 1 should be larger than the measure of angle 2 by itself because you removed the measure of angle 3, which has to be a positive number. The measure of angle 1 is also going to be larger than just measure of angle 3 by itself because you have now removed the measure of angle 2. And that's what we get down here. So that is the corollary to the triangle exterior angle theorem. So I want to go over this example in which we want to determine which segment is the shortest in the diagram. So now, the immediate reaction to this problem would be to quickly jump to the conclusion that, or the assumption that, well, because 43 degrees is the shortest or smallest angle in this diagram, that would mean that AC has to be the shortest side. But as Lee Corso says, not so quick, my friends. What we also need to compare is that we have two triangles that have been put together, and we have this angle is 46, this angle is 47, so this 47 degrees is larger than 46 degrees. So this 47, this AC, isn't the shortest side in this triangle ABC. In triangle ACD, this would be the shortest side. But the issue is, because this side is shared, and this triangle says, no, that's not right, we then have to go ahead and look and say, well, this one says 46 degrees. Well, 46 degrees would tell me that BC is actually the shortest side. So now you might be going, well, what happens in the off chance that, let's say instead that they don't tell me this is 43 degrees. So we'll get rid of this. And then we'll say, well, what if this was actually the 43 degrees here? So this was 43 degrees, and then that was 46 degrees. Well, what would happen then? And the answer is we would not be able to tell. On the previous problem, because one of our triangles said that a shared side was the smallest, and then the other one said, well, actually this other side is the smallest, we were able to kind of piece that together. Here, this triangle says this is the smallest side, and then this triangle says, but this is the smallest side, and therefore I say, I don't know. So let me just quickly erase this and just kind of diagram this out. So, the triangle on the right says this is the smallest side. Well, but then this triangle says, actually, you're wrong, this is the smallest side. And this only works because one of my triangles is pointing to this shared side. If it didn't point to a shared side, then we would not be able to determine the actual shortest side of this triangle. So that covers inequalities in one triangle. We went over the triangle inequality theorem. We went over some more statements about comparing sides to find angles and angles to find sides, along with the corollary to the triangle exterior angle theorem.